Good morning, everyone. I want to welcome you to our Green Hydrogen Special Lab event. And I think this is our first one, right, Constance? This is a new lab. So welcome. We're so excited to have you guys here with us today. If you're able, turn those cameras on. We love to see you and engage with you. We'll have plenty of time throughout the day for you to tell us about what you're doing and all the failures and the triumphs, right? I have an incredible engineer to introduce you to who will do the introduction and get you started. So I will hand it over to him, Mr. Eric Einset.
Thanks very much, Jillian, and thanks everybody for joining here. I'm pretty excited. This is a lab I think is really cool, and not only do I hope you have a really good lab day here today with us, but you're also going to get a chance to meet some really cool people. So we have Sophia and Catherine, who are engineering college students that you can talk to and ask questions about what it's like to be in engineering school. And then we have a really amazing special speaker at the end of the day, Dr. Adria Wilson. And you're going to learn so much. She's done so much, and she's very much in the field of carbon reduction, and she's going to tell you a lot of stuff, which is going to be really good. So my name is Eric Einset. I'll give you a little bit more background later on when we do some Q&A of my background. But I am a chemical engineer. I worked for over 30 years in engineering, in various engineering jobs, various engineering companies. In fact, one of the last things I did here, just last fall, I was working in some green hydrogen, on a green hydrogen project. So what we're going to do is give you some background about green hydrogen.
Sure.
I think we have to go on mute if you would. We'll give you some background on what is green hydrogen, but more importantly, before we even get to that, we're going to talk about decarbonization. And what you're going to get a chance to do is actually create and make some green hydrogen. You're going to be making a little chemical reactor. But don't worry, it's hydrogen, but it's a very small amount, and it's not going to be dangerous or anything. So don't worry. I know that sometimes that question comes up. But what we'll do is you're going to actually make a chemical reactor. And what I want you guys to do as you're thinking about how to construct this chemical reactor, I want you to be really creative about how you can get as much hydrogen out of your electrochemical cell as possible. But let's get started on the actual background material here. So I'm going to try to see if I can figure out how to share my screen. And we did practice this earlier. We'll have to see if I learned anything from, it's not that one. Where is it? Maybe a second here. That's got to be it.
Yep, it's coming up right now, Eric.
It's coming up? Okay, excellent.
Yep,
Excellent.
perfect.
And you see that?
Yeah.
All right. So we're going to talk about green hydrogen, but actually, really, the big part, the background of this is all about decarbonization. Oh no, I think my Zoom just quit unexpectedly, so I might have to reshare this.
We've got
Okay,
you.
we can see it.
We can see
You can see it?
Green, yeah.
Yeah, okay. You keep me up to speed here on if you can still see me, because I'm getting some errors.
Will do.
So basically, as you know, our lab are all developed by engineers, and also we present them as engineers. So as I said, I'm a chemical engineer. My background, as you can see here, the years I've worked, and also Grace and Al.
Froze for just a second.
Yeah, am I back?
You're back.
Okay.
I'll
I
smile.
think I'm gonna. Okay, I think I'm gonna have to get a new laptop at some point here. Okay, can you see my screen?
All good. Yep.
Okay, so let's start with what is decarbonization. So essentially, decarbonization is all about reducing or eliminating carbon dioxide or other gases that cause atmospheric changes from what we do every day. So it's basically reducing our emissions of harmful gases. And so in order to do that, you want to understand where these gases are coming from. So first of all, let's talk about why this is important. So engineers work with a lot of data and information, and I'm going to show you a bunch of graphs. Now, I don't know if you like math or if you like graphing stuff, but this is really a way that engineers try to explain what's happening and how things work. So on the left-hand side is a plot of the carbon dioxide in the atmosphere for 40,000 years. So as you can see, the scale on the x-axis is 40,000 years backwards from zero, which is today. And you can see that carbon dioxide kind of naturally varies over time. There are cycles. We have weather cycles. We have cycles in our atmosphere and in how the Earth evolves over time. And you can see that it kind of varies from, I guess, around just under 200, maybe 190 parts per million in the atmosphere, up to, in the upper 200s, maybe 300 parts per million. And that's kind of the range of how CO2 has varied over time. But if you look at the very edge of this graph, you'll see that we're kind of spiking compared to the last 400,000 years. So people may say, oh yeah, the atmosphere varies anyway, it's natural that you'll have high levels of CO2, but we haven't seen this type of CO2 in forever, honestly, in the life of the Earth. So if you look at the very edge of that plot, the thickness of this line is probably several hundreds years. So what I've done is I've actually given you another plot on the right-hand side here, which gives you the carbon dioxide levels just over the last, say, 250 to 300 years. And this plot shows two things. First of all, it shows you in the red, the atmospheric CO2 level. So that's the same as that was on the left-hand side. So that's kind of in red or pink. And you can see back in the 1750s, there we were at around 280, and it's now starting to drift upward. Now, the other line on this plot is actually a calculation of the emissions from Earth, from mankind, if you will. So it used to be very, very, very low because, in the very, very, very olden days, there were no machines. We were just burning wood for fires to keep warm and things. But when the Industrial Revolution started, we started to pick up more and more, basically, emissions. We were producing more and more CO2. And then you can see kind of at the late 1800s, early 1900s, we started to get more and more CO2, putting more and more into the atmosphere. And it appears that the levels that were measured in the atmosphere are now starting to go up along with the levels, the emission rate that we're actually putting it in. So most people would argue that this is probably the cause and effect here. We're seeing an increase in CO2 levels because our industrialization is putting the CO2 into the atmosphere. So the bottom line is that the climate appears to be changing. We're especially seeing it over the past 20, 30, 40 years. And when we're seeing a much more severe weather events. And we do know that CO2 levels are continuing to go up. So it's most likely that this increase in CO2 or other greenhouse gases, what we call GHGs, is related to this changing climate that we seem to be seeing. Sea levels are rising. And severe weather events are occurring more and more frequently. So, we talk about how engineers are problem solvers. We engineers take the basics of science, fundamentals of physics and chemistry and biology and also math, and we try to solve problems. So this is a problem. We have a change in climate. And it appears that mankind is a driver of this. So how do we try to solve this? So if you're going to try to solve a problem, you have to understand what's the root cause of the problem. So the first question you may ask is, well, where is all this CO2 and greenhouse gases coming from? So the next plot here I have is showing you essentially where in, in what countries are actually producing the most greenhouse gas emissions. And as you can see, this is actually a Pareto chart. And a Pareto chart is basically a bar chart that is kind of ordered by the highest to lowest impacts, if you will. So you can see that China, it turns out, is actually is the largest driver of greenhouse gas emissions. And that's not really surprising. China in the past 20 to 30 years has really been industrializing on their own. And they've brought, millions, I don't know if it's billions of people out of poverty. And there's a lot more of a middle class now in China. These more affluent people are wanting nice houses, so they're wanting nice cars, they're wanting more things. So it's not surprising that China, and as a result of their very rapid growth in their economy, is one of the big drivers of all this new emissions. But as you can see, kind of the traditional countries, if you will, of the Western US and Europe, they are also very high on the list. Although I have to say Europe has been very aggressive in trying to reduce their emissions. But you can then see through the rest of this plot where the big drivers are, or at least which countries are the big contributors to greenhouse gases. Now, the other thing I want to show you about this is this little chart here on the side. It's called the Kyoto gases, and it shows you that carbon dioxide is not the only greenhouse gas. It's the one that's we talk about the most. That's the one that we measure the most. But there are other gases that also have the same impact on global warming, or climate change and the increase in temperatures across the globe. And what's kind of interesting here is that if we take CO2 as an impact of 1, for example, release or increasing methane. Methane is another greenhouse gas. It's 20 times more harmful, or it's equivalent to 25 times the CO2 impact. And when it comes to greenhouse gas and warming potential. And then you can see that there's some others like nitrous oxide, which is 300 times more impactful than CO2. And then you can get into some of these fluorides and more complicated molecules, which are thousands of times more impactful than CO2. So all these things, when we talk about greenhouse gases, we're talking about all these types of gases that we want to be prudent and try to reduce all of them. And in particular, these really high impact ones are the ones that we want to be particularly careful of. So those are the kind of the countries and where the gases are coming from. But let's ask the next question. If we wanted to reduce and do something about all this, we need to know exactly what industries, what are the things that we do that drives the greenhouse gas emissions. So the next chart gives you now this is a pie chart. It kind of breaks down of all the greenhouse gas emissions in the world. This breaks down where they're coming from. So let's just look at some of them here. So let's start with electricity. So this says that 26% of all the greenhouse gas emissions are coming from the production of electricity. So you can see the breakdown here is there's still many places around the world that use coal-fired plants to make their electricity. Natural gas also has emissions, but again, the electrical grid, or rather the production of electricity, is a big driver of greenhouse gas emissions. Now let's jump over here to transport. So all the cars and trucks on the road that are using gasoline or using diesel, those are a pretty big contributor to CO2 emissions and production of greenhouse gases. There's also, you can see aviation, that's airplanes, and ships. A lot of ships transporting goods all over the world. They're also a non-zero impact on greenhouse gas emissions. Now I'm gonna talk about the industry a little bit later here, but let's a last one. Let's look at buildings. So basically, the energy that we use to heat our buildings has some impact. And then you may not realize, but also just agriculture and the livestock. they do have a non-zero carbon footprint. So depending on the crops, you may have noticed that there was a nitrogen-based material in the previous slide that has a pretty high greenhouse gas impact. So that comes from kind of just crop management. It doesn't mean we have to get rid of crops, but again, good crop management can reduce those levels. Livestock, you may have heard about, in cattle, they have a certain process that they produce methane in one of their stomachs, which is actually not, again, a non-zero impact of or non-zero contributor to greenhouse gas emissions. So these are all the industries. So these are all the places where CO2 and greenhouse gases come from. So the real question is, what can we do about this? And again, as engineers, you have to think about, what are some solutions here? So you probably realize we can, and we're doing this already. We're trying to replace as much of our electrical grid and electrical generation with renewables. So that's why you see a lot of solar energy, you see a lot of wind energy, and these are all alternatives to coal and natural gas to provide electricity. So when we flip on a switch, the light comes on. Now for transportation, you're probably also seeing there's more and more electric vehicles out there. And also the use of sustainable fuels for aviation is a very small, but potentially and possibly growing area. But all this initiative to try to take carbon out of a lot of what we do is something that's called the energy transition. I don't know if you've heard that term before, but it's a huge undertaking that the world is trying to do here, and to try to convert all of our electrical generation to renewables, trying to convert our transportation to battery-based or certainly low carbon based. By the way, the batteries would have to be charged with renewable energy. So this is a big deal, and the energy transition is going to be something that's going to be part of your lifetimes. And opportunities for great jobs as engineers and problem solvers going forward. So let's talk a little bit more about that piece of the pie that I kind of skipped over, which is the industrial greenhouse gas emissions. Now this is a tricky one, because you can't just do one thing. You can't just convert to renewable energy. You can't just get everybody to drive electric vehicles. There's a lot of different things that drive this. So when they make iron and steel, they use these very, very high temperature blast furnaces, and they reduce the iron ore. And a lot of these reactions require hydrogen, or they require a lot of energy for sure. In producing oil and gas, there are just natural leaks from wells. And sometimes when a producer is producing oil, they get some gas with it, but they're not interested in the gas, so they just burn it off. That's, again, it's producing CO2. If you are mining coal, and as you could see, there's a lot of coal being used in the world today, that the coal beds actually have methane in it, because it's just another hydrocarbon that comes along with coal. So that's being released. When they make cement, they again have these high temperature kilns, and they use some hydrogen and various materials to produce the cement. In chemical production, hydrogen is used in making ammonia and methanol and fertilizers. And in refining, they use hydrogen, and in other industries. And by the way, we're not saying that electric vehicles are perfectly green, because there is some production of greenhouse gases in producing batteries. So I would challenge you and to basically go and research on your own. What is the true carbon footprint of electric vehicles? But some of the common themes in all these things, I hope you see, is hydrogen. Hydrogen is a really important material in our industrial world today. And I'm gonna basically, the way traditionally the way hydrogen is produced is starting with methane, and actually the hydrogen production process generates a lot of CO2. So finally, we've gotten to green hydrogen. We're finally getting to what's hydrogen got to do with all this. And that's where we are now, is that one of the ways we can get at some of the carbon footprint of all these industries is by promoting and basically developing hydrogen in a different way than it was normally been done. Okay, so let's talk about hydrogen. So today, most hydrogen is produced with CO2 as a byproduct. So if you're in a chemistry class or you've had chemistry, you might like some of this, some of these formulas here. So basically, typically, hydrogen is formed by steam reforming. And essentially what you do is you start with methane, which you can see over here in the equation, and you react it with water, and that gives you CO and 3 hydrogen atoms, molecules, sorry. So what then happens is that CO goes in and continues to react with hydrogen, or sorry, with water, and that forms now CO2 and another hydrogen molecule. So the net result is that methane, together with water, produces CO2 and hydrogen. Bottom line is that for every pound of hydrogen that you produce, you actually produce 22 pounds of CO2. So that's quite a bit of CO2 that you're generating. Now there's 2 ways of doing this. On the right-hand side here, you can see something that we call gray hydrogen and blue hydrogen. So gray hydrogen is just what I described. So the methane goes in, the water goes in with it, or steam, you produce hydrogen and you produce CO2. Now, that is a dirty form of hydrogen, gray hydrogen. That's why they call it gray. Now, if you actually took that CO2 and you captured it and you put it and buried it so it didn't go into the atmosphere, that is a better, lower carbon footprint form of hydrogen production. And that's called blue hydrogen. So there's a lot of research going on in how best to manage carbon capture and the capture of carbon dioxide. So those are 2 of the types of hydrogen that they talk about. But green hydrogen is actually based on a process called electrolysis. So this is an example of an electrolysis cell. And the way it works is that you have water, which obviously has hydrogen and oxygen in it. And what you do is you run an electric current through it. And that electric current in the water then breaks the water down and forms hydrogen gas and oxygen gas. And if you're using clean electricity or electricity that is from a renewable source, there should be no CO2 production as a part of this. All you're producing is hydrogen and oxygen. So that sounds really great. To do that on a large scale, you need a large plant. And here's an example of a very large hydrogen production plant, a green hydrogen production plant. So the beauty of this process is that it's for every pound of hydrogen you produce, you don't produce any CO2. So the process is just, as you can see here on the right-hand side, the electrolysis process, but it's a very small level. So let's talk about the production of hydrogen and kind of the overall scale of things here. So green hydrogen the idea is that you would have green hydrogen produced, or electricity produced by renewable sources that goes to the electric grid. That can power your electric vehicles. It can power your heating, for example, through heat pumps and things like that. And then that part of the electricity goes to an electrolyzer in an electrolysis process with water. That green hydrogen then can be used in the chemical industry to produce chemicals and fertilizers and things. It can be used to produce other fuels. So, for example, green sustainable fuels and for sea vessels and land vessels and air vessels. And this is all very, theoretically very nice, but it can only work if it's economical. And this is, again, where the engineer has to understand what are the economics about these processes. So what we have here is a question of, can you make this economical enough that it'll actually happen? So now let's get to what you're going to work on here. So you should have in your kits, you should have some materials here, and it's a very simple process. Hopefully you've got a plastic water bottle or some kind of container that you can put some water in. And then we've given you, or you should have a clear straw. And what you're going to do is you're going to use that straw to capture the hydrogen. So I'll show you in a bit how that works. Now, the way that you're going to create your electrochemical cell is that you're going to use pencils as your electrodes. So you're going to have electrodes. And those electrodes will be connected to a battery over here using jumper wires. And what you're going to do then is essentially create a hydrogen cell. Now, the way this is going to work is that it's going to look something like this. You're going to have, again, your two electrodes hooked up to your battery. You're going to be producing gas, and you're going to be essentially making a tube that you can collect the gas in. Now, I actually have a little straw here. Can't see it. It's not clear, so it's not as good as what you have. This turns out to be a paper straw. Well, what you're going to do is you're going to seal one end. You can either put some glue in the end or pinch it off and seal it all up, because it has to be totally sealed. Then I want you to turn it over and fill it with water. And once you filled it with water, put your finger over it, and you're going to dip it into the little well of water that you have. And then if you let go, the water should stay in your straw. And then what you're going to do is you're going to create your cell, and you're going to produce gas, and the gas is going to bubble up and displace the water. It'll displace the water in your cell, and you'll be producing green hydrogen. So that's the idea for today. Here you can see the material, the chemical reactions, and that's really where it is. So now, if you want to do something kind of tricky here, what you can do is put some salt in your water, and you're going to have chlorine and sodium ions in your water. And when you then produce your cell, you're going to actually produce gas, and you're also going to produce chlorine gas, and you're going to be able to smell that. Excuse me for a second. And when you do that, I want you to smell the water to see what it smells like. So let's stop at that point and see if you have get you started basically on your work here, and then we'll come back and see how you're doing. So Jillian, can I pass it back to you for a minute here?
Yes, I don't think I can follow that. That was an awesome introduction by Eric Einset. Thank you so much. And I think you got them ready, Eric. I can tell they're ready to get their hands on these kits and get started producing some green hydrogen. So let's go ahead and open up the breakout rooms. We'll have ET staff in there, some college mentors to guide you. Let us know if you need any help getting into the breakout room. There's one. And we'll see you back here at 11:30 to show us what you've done. Okay? See you soon.